So I've received lots of private messages from you guys on LinkedIn about what I think about this lamp experiment with long transmission lines that can run to the moon. And so I'm going to weigh in on this today, but first I need to make a few clarifications. So first, there's a difference between whether or not this lamp is an incandescent lamp or whether it's an LED, and I've seen examples from you guys of both, and they're different. In an incandescent bulb, instantaneously before the bulb gets warm, there's a low cold resistance, and so initially it'll have a higher current, and as it warms up, it'll get a lower current, higher resistance, and that happens through its thermal mass. And so there'll be different impedances as a function of time as that lamp gets powered. In the case of the LED, it's a very nonlinear function of V versus I, and there's different large and small signal impedances, and the impedances will be different for different colors. They'll also be different for different powered LEDs. For those of you that are interested, I did do an article a year or so ago in All About Circuits about LEDs, and I'll show you that link in the next slide. But in any case, this resistance isn't going to be constant, and it's also not going to be linear. So thanks to William Shockley, we can characterize the voltage versus current curve of the LED using the Shockley's equation. And the Shockley's equation is an exponential function that looks something like this junction voltage equation. You might remember this from your small signal theory, because if we evaluate the small signal junction impedance, which is the derivative of the voltage with respect to the forward current, we end up with 26 millivolts divided by the forward current, but also multiplied by the emission coefficient N, and we add the junction resistance. You might remember this from small signal theory in school, which was for Class A amplifiers, 26 millivolts divided by IE. And this is similar, but a few minor details. One is that in a small signal junction NPN transistor, the emission coefficient is 1, so we don't need to include it. In all other junctions, it's not 1, so we do. And of course, that simplification also assumed that the junction resistance is 0, and it's not. There is some finite bulk resistance in the junction, so to be accurate, it would be RJ. That's the small signal impedance. What I'm seeing a lot of people showing is the large signal impedance, which is the voltage of the LED divided by the current of the LED, and that has little to do with instantaneous impedance or matching. Here I set up a very simple experiment where I put a DC current into an LED, and I also added 1 amp of AC current so that we could measure the voltage. For those of you that are not simulator experts, the example doesn't actually use a 1 amp signal. It takes the derivative of the LED function, multiplies it by 1. So it's just a neat trick that we can set the current to 1 to get directly what the impedance looks like. We're not really putting an amp there. In the DC case, I can do that sweep very easily as part of the DC simulation. In the AC simulation, I can't, so I added a parameter sweep to allow us to sweep the LED DC current from 1 milliamp to 100 milliamps. Here's that link I mentioned in All About Circuits if you're interested in looking at the characteristic impedance of LEDs or how to model them. Anyway, running this simulation results in these two curves, the red being the large signal impedance and the blue being the small signal impedance. And you'll see that they're both linear on a log-log plot, so neither one is linear, and they're also quite different from each other. And so that's challenging because as the LED powers up, it means that we're going to be reflecting different impedances. And since the response in the transmission line is a function of the impedance matching, the impedance match is going to change with time. Now, first, let's dispel this whole idea that instantaneously the capacitance in the transmission line looks like a short circuit, and so you're going to get this huge spike of current. That's not true. If we take this pulse, I set a pulse through 50 ohms, that would look like a TDR. I'm measuring the current at the cable input so we can see what the current actually looks like. And then I placed a 1 microsecond transmission line with the far end shorted. And if I run this for 5 microseconds, you can see that instantaneously the TDR voltage is 2.5 volts, half of the 5 volt pulse, meaning that we perfectly match the 50 ohms to the 50 ohm cable. That's a given, of course. Transmission line is 1 microsecond, so we're going to see the round trip at the TDR, and that says that we see 2 microseconds at 50 milliamps. Why 50 milliamps? We had a 5 volt source that says we have 100 ohm impedance to get 50 milliamps. And that's true. Instantaneously, we see the 50 ohm resistor, and we also see that in series with the 50 ohms of the cable. Once we get through the reflection in the cable, you'll see that the current increases because now we do see the short, and it goes up to 100 milliamps, which is 5 volts divided by 50 milliamps. So there you go. Just to prove the point, I also want to do it in an open circuit, so I removed the short from the far end of the cable, and you can see we still get 50 milliamps for the 1 microsecond through the cable and the 1 microsecond back. And at the end of that time, we see the open cable, voltage goes up to 5 volts, current goes down to 0. And so, again, there is no current spike due to the cable. What we see is the characteristic impedance. Now I can also use a simple example like this. So now I have the pulse going through 50 ohms, and I have 2 transmission lines, one between the pulse and the diode, and then another one between the diode and the far end of the cable, which we can either open or short. I have a diode model here, I have a transient simulation, and I have slider bars so that I can set the length of the total cable. I can set the length on either side of the diode by changing the location of the diode. Right now it's set at 0.5, which means that I'm right at the midpoint of the cable, and I set that cable as being 1 microsecond long. I could put the current probe on either side of the diode. It's a 0 insertion impedance, 0 length line, so it wouldn't really make any difference. If I included the electrical length of the LED, then yeah, theoretically it would make a small but finite difference whether or not I looked at the current going into the diode or coming out of the diode. For our purposes, they're exactly the same. So let's go ahead and take a look at what that looks like in simulation. So here is the simulator, and you see initially I shorted out the diode and I opened up the short at the far end. So I really just see 2 cascaded transmission lines, and you'll see I put the current probe in the middle. I have a 5 volt pulse. It's connected through 50 ohms. And so now I can look at what the current through that pulse looks like. And again, I can vary the 50 ohm source resistor that feeds into this first cable. I can vary the electrical length of the total line, and I can also move the location of the diode within them. So let's go ahead and run this real quick, just so we can see what this looks like. So now I'm running into an open cable. I have the small signal and large signal impedances here on the right, and I'm looking at the pulse current, and you'll notice in this pulse on the left hand side I got 2 plots that are the same except for the scales. One is 10 times the scale of the other. So in the near term you can see that I have a 0.5 microsecond delay before I get to the first cable. That makes sense. It was halfway to a 1 microsecond long cable. And then of course the LED current goes up to 50 milliamps, which is the sum of 50 ohms plus the 50 ohm characteristic impedance of the cable. That lasts for 1 microsecond, which is the round trip through the second cable, and then that current goes to 0. If I go ahead and set this to be a short, I can remove this open and make it short. And now I can run that simulation again. And you'll see it looks similar now, where halfway through the line we get up to 50 milliamps, and then that lasts up until we get to the reflection both directions of the line. And then I should be able to there you go, show you what it looks like at 100 milliamps. And so that 100 milliamps now is because we have a short at the other end of the cable. So now we see the 5 volts divided by just the 50 ohm resistor. And you can see in the midpoint, we're right in between. This is what a TDR would see, and that says the reflection is 0. Now let's move stuff around. So we'll go run this simulation one more time. I'm going to disable this first so I can open up the diode. So now we're going to see the diode. Oops, I forgot to open up the diode. There we go. So now the diode is open. And now, of course, we have this variable impedance through the LED that's going to change as a function of the current through it. And let's just rerun that simulation with the diode in place. Okay, and now you can see here is the current, and we can see the two different scales. We can also see the LED, and here I'm monitoring the LED current and the LED power, and you'll see that at a half a microsecond, the LED power goes up to 50 milliwatts. It's not the maximum. It actually hits a little bit more than, maybe about 130 milliamps, and you can see the one reflection in it. Eventually, it'll settle out at 100, a little over 100 milliamps, and that is due to the 50 ohm resistor. Anyway, you can see the reflections. Now, if we want to move stuff around, we can move the electrical length. And you'll see as I move the electrical length, where it is that the LED starts to see power moves. So if I move it closer to the poles, then it happens sooner. And if I move it further from the poles, then it happens later. And if I put it back in the middle, well, it'll happen right at that half microsecond at the end of the first cable. But you'll notice the reflections didn't change. The only thing that changed was the time spans. Now, if I change the 50 ohm pulse source, now you can see I can get some really interesting looking waveforms. But again, the LED is going to see power at a half a microsecond, exactly the point that it gets through the first delay line. Now I've only got about 10 milliamps in the LED, so it's going to be dim. And after a microsecond and a half, it's going to get brighter, and then it's going to get even brighter. Then it's going to start to get dim again. And here you can see the LED current. And so as we move this impedance around, we can get all kinds of different pretty pictures. Here I can generate a staircase with an exponential waveform. But it really all depends on how well the match is. I can't get a perfect match because the LED impedance is a function of time because of the current through it. And so we can't have the characteristic impedance match that at all times. It's only going to match it at one time. Now, if I move the location, you can see I can move that also. And as I move the location, you can see the reflections take longer. The pedestal there lasts longer, because it's the round trip of the second cable. And you can see we get the current in the LED sooner because the LED is now closer to the pulse. The closer we get it to the pulse, the better off that's going to be. Now, if I change the resistor, you can see again, I can get all kinds of wacky waveforms, and that's just a function of how well I do or don't match the cable, just like the series resistor before. But where it is that the LED occurs is going to be independent of that, and it's always going to see power at that half microsecond or wherever it is that the first cable exists, whatever that delay is to the LED. That's how long it's going to take before the LED lights. Now, we do have to define lights because you will actually get lights from the LED at this 5 milliamps that occurs here in a half a microsecond, and of course it'll be brighter at 35 milliamps and even brighter at 50 milliamps. So the intensity of the lamp is going to change with time, up until we get to this 50 microseconds. And once we get to actually here, you can see around 20 microseconds or so, maybe even 15 microseconds we can call it, which is a little more than 10 line lengths. Then it'll stabilize. But up until it gets stabilized, we'll see the LED light after the delay of the first cable. We'll see some really wacky responses based on the matching or mismatching of the system, and eventually settling out to the resistance that's defined by the resistor. Anyway, that's my take on it. And if you want this ADS workspace, let me know. Happy to send it to you.